Morning, everyone. Welcome today to the second workshop. Just want to make sure before we begin, is the screen showing and is the audio all fine? If someone could please just put it in the chat. Okay, perfect. So today I wanted to cover the most important part of when it comes to starting a project where we're going to be using AI and machine learning. So the first thing is talking about data and what are its different types. And the second thing is that once we've got our data, how can we process it for our models? And what kind of methods are there and how do we do it? And then what are the different types of models that we could use using our data? One extra thing I wanted to talk about is how we can use prompt engineering to help us write code. Of course, not everybody is a programmer and has lots of coding experience, but we have lots of tools now that we can leverage to help us write code. And finally, what is a machine learning pipeline and how can we use it to build AI? So very briefly, last time, we looked at the definition of machine learning, and that was algorithms which learn patterns in data to make predictions. And the example that we used is, say, where we to collect pictures of dogs, we're able to annotate with bounding boxes where the dog is in an image. And then we can select certain features like its mouth, its ears, its nose, its face, things that we know are very similar between the same breed of dogs and other types of dogs, so that when we give it to our model and we give it a new image of a dog, it's able to detect that there is a dog in this image, even if it's not the same breed as one we've seen before, because they have very similar features. And of course, that we give it information and feedback that when we give it images that aren't dogs, that we don't detect them like we see here, and instead we detect them as cats. So the most important principle of machine learning is this idea, this concept of garbage in, garbage out. So if you have a machine learning model, no matter how powerful it may be, if your data is not useful, if your data is not in the correct format, if you haven't processed it in the most optimal way, you're always guaranteed to have this rubbish output. And it's very simple, really, because if you trained a model on, say, English language, and you try to predict it a different language, German, it's not going to be able to do that because you never gave it that information in the first place. And obviously, it's more than just is the data the correct type. It's also to do with how we can process it. So let's talk about the different types of data. You have numerical data, pictures, videos, text, and audio. And these are very broad categories for what data can be. So we go into more detail and we look at numerical data. So you could imagine that we have a very simple 2D table, a simple table with x values and y values, right? And here we can see that we've got 4 different values for x1, 2, 3, and 4, and 4 corresponding y values, 2, 4, 6, and 8. And what we can do is we could plot it on a graph, right? So we could plot for the first one, the second point, the third, and the fourth. And maybe now we want to build a model. And so what we can do is we can line up those points and we can say roughly this line is y is equal to 2x. And what that means is if we have a new value for x, say 5, we could plug that into this, x is equal to 5. We can plug that into this equation and will give us the correct value for what the y value should be, which will give us 10. And obviously this is a very perfect model. It's very rare that your data points will lie on an exact line that we can use to predict a new input every single time. But the most important thing is that data in machine learning models has to be converted to numerical data. So when we've got images, we have to somehow convert this into numerical data that we can use for our models. Well, images are just made up of lots of these tiny, tiny pixels, and these pixels essentially are just different combinations of red, green, and blue. These are the primary colors of light, and with different combinations, we can produce all the different colors across at least the visible spectrum that we use in computer screens. So we can take this image and we can break it up into all of these small little chunks, all of these rows and columns, all of these very, very small pixels. And what we can do is we can look at each individual one, and what that will give us is a single triplet of its color in R, G, and B, so red, green, and blue. Right. So as an example, the top left corner will have this value in hexadecimal. That's not very important. But the main thing here is that we have these three numbers, right? So the amount of red, the amount of green, and the amount of blue. And if you combine these together, it will give you this color. And this is what we can give to our model. Of course, there's videos, and videos are just as simple as just many, many images stitched together. And usually in models, what we do is that when we give it a video, we always give it the previous frames. So if I'm running a model on this video, at this time step here, what I would do is I would give it not only this image, but also the image before it and the image before that as an example. And that would help it, let's say, predict or to solve what it is that I'm trying to get in the next image. Text is probably the most complicated and the most difficult kind of data to work with. And usually it's because it's unstructured, right? So unstructured text is when you've just got this random free-flowing text and it's not very clear, like we had in the numerical data where we have specific values for X and specific values for Y. It's just blobs of text. And obviously we can try to break it down. So there's this concept of tokenizing, and all you have to remember is that there's different ways that we can break down sentences. We can either split it up so that every letter we can have separately. We could also have each word separately, or we could have this idea of subword. So when you look at the word tokenizing, we could break that up into token and izing, because maybe this is a suffix, so a combination of letters that we can add to the end of a word that we could have for other words, right? So you could have it resizing, right? And in that idea, we can reuse this because it has multiple meanings. And same with token, because we could put token in front of tokenizing, but token itself is a word, so is tokens, etc. And now if we take each of these characters, right, all these subwords, all the words by themselves, we could assign a number to each of them. So in this example, we've said that the letter A would be 1, right? And then letter B would be 2, and the letter C will be 3. And in this way, we can now have a numerical representation for all of the letters in the alphabet. But the problem is that if we try to understand the differences between, let's say, faster and fastest and quickest, you'll see that the numbers are very, very different, right? Even if we were to put it into these subwords or words, these numbers are very different. And we don't want that. What we want is this idea that words have relationships with each other. So if I look at the thing that takes, say, in our understanding of what goes from man to king, right? Maybe that would be the word royal, right? This idea that, with royalty, we could say that a king is just a man plus royalty. And that would be the same thing if we were to go from, let's say, woman to queen. And we can do more than that. So we could look at each of these words and we could say, well, what are the definitions and what do these words mean, right? So for example, for king, what we see here is that we'll have different features, right? So here, one example is living being, feline, human, gender, royalty, verb, plural, etc. And so what we do is rather than just drawing a word by itself or every letter as a number, instead, we have representations for what words are. So as an example for king, you see it's very high for royalty. It has a very high score in royalty. And these would be between -1 and 1. So 1 would be like a really high, strong correlation. And let's say a -1 is a very weak correlation. So as an example for queen, it says the plural is -0.9, which makes sense because queen is singular. Queens would be plural. So for that, maybe you'd have a full number 1. And these things, these different words here, is what we call word embeddings. And of course, we can have much more than just the 7 here. This is just an example. Here's another example where we show the first example that we had already. But you can see here where we go from this verb walking, right, and this verb swimming, that if we apply this idea of tenses, so if we go into the past tense, the word that we get, if we apply that to walking, would give us walked, because walked is the past tense of walking. Same with swam. Swam is the past tense of swimming. And it's this idea that we can go from different words to other words by understanding the different relationships. So here it's the countries of the world and their capitals, their capital cities. And this is really useful because now we're kind of starting to have an understanding of language. And of course, we can do this for all different languages. It doesn't just have to be English. We'll move on to the final type of data, and that's sound, right? And sound is a little bit different from all the previous kinds of data because sound isn't necessarily perceived just on the screen. It's something that's in the physical world, right? So there's sound waves that come into your ear. And these sound waves have different properties, right? So how loud it is, how quiet it is, how deep and how high pitched. But essentially, when we take these sound waves, we can plot them onto a graph, and we can just convert them. And the thing that we are most interested in is this numerical representation. So there are people that are working, let's say, on, using a person's speech by just them speaking or saying a specific word. We can look at the different properties of these bars, essentially, in this bar chart. And from that, we could detect, let's say, whether they have throat cancer or not. And similarly, maybe we use this for translating languages. So by listening to a speech in English, we can then use this graph and we can take these numbers of each of these bars and we can use that to, let's say, convert it to Arabic or Spanish, etc. In general, those are the main types of data, these main types of data. But what we have to do in every single situation is we have to bring it back to this numerical data. So we have to find a way to convert all of our data into numbers because models, our machine learning models, they run on computers. And computers can only work with ones and zeros. And that's what we call binary. Binary just means an option of two options, two choices. And in computers, that's one and a zero, right? Either something is on or off, etc. And with numbers, we have a really good way of being able to use binary. But for images, it's more complicated, right? Same with videos, same with text, and of course, same with sound. Once we've got our data, the next step will be the data pre-processing. So each of these different types of data will have their own different types of pre-processing. And of course, it will be difficult to cover all of it. So I thought I would just go through some examples. And the most common one will be missing data, right? So missing data is where in our data sets, so from, let's say, the images that we've collected or the, let's say, survey responses that we've collected, there will be some records in that which are missing, right? They won't have a value. And the number one thing we have to do at the very beginning is understand the reason why do we have missing data. And it's the most important thing. So as an example, this is a data set of the physical characteristics of breast tumors. So what this is looking at is, in terms of those which are cancerous and non-cancerous, can we look at, say, its width, its height, how smooth it is, how, let's say, how many black pixels there are, because maybe it's darker in a scan image. And what we can do is we can just show all of the different scans. So let's say here there's a few hundred, and we have all the different properties, right? So like I've just mentioned, with the width and the length and the depth, etc. And what we can do is that if a value is missing, we can just color it in yellow. And the idea is now that we can just visualize, right? So we can create a graph that lets us see the missing data. And this is something that you should always do whenever you begin, is to visualize your data and look at where are your missing data. And if I was to take every row from here, which had a missing value, I essentially get this graph here. And now what I've seen is that missing data, it wasn't just random. It's clear that certain features are completely missing from these, say, 30 samples in my data set. Now, when we've got to this stage, the final step is simply either removing them or imputing them. Sometimes when we collect data and there's missing values, we would love to be able to use the entire, the other features that we've collected from that data, but maybe that would skew our results because let's say that feature was important in the first place. And so in that case, we could remove it, just entirely remove these from the data set so they're not there anymore. Imputing is this idea that, well, say I can look at the average. So what is the average width of all the different cancerous tumors? And what I can do is I can just make all of the ones which are missing the same as the average. And it's a very common technique that we use in machine learning, and that's just imputing the missing values by the mean. And of course, there are different methods, and we can go. People can make this a much more complicated problem, especially when you've got lots of missing data, because then you don't want to just remove all of the ones which are missing, because it will be very common to have that. But the main thing that I want you to remember is that just understand why do you have missing data first. And there's lots of resources online, so that if you were to search up why, if you have a specific reason for having missing data, why is it that you have it, and what have other people done? What other techniques have they applied to be able to solve that issue? The next kind of problem that we have to solve in data pre-processing is when we've got noisy data. So as an example, here we have a lot of scatter points. So each of these points will be a measurement of the height at a specific time. Right? So you can imagine that this is a sound wave or something similar to that. And the problem is that all of these data points are really, really close together. And so if we were to build a model, we would want something that, generally represents the distribution, right? So roughly we can see here the shape of this, of the data points that we have. We don't necessarily need to be able to detect these outliers, the ones which are really far away from the rest of the data. What we want when we build our machine learning models is to just be able to recognize the patterns, right? That was the whole point of machine learning, is that we were able to build algorithms to detect the patterns. And in this case, what we can do is we can get rid of this extra noise. So these extra values, which are essentially just padding out this line, because it will become really difficult if we were to say take the number 4, whether or not we tell it to predict a -5 or whether we tell it to predict a 0. Because of course here we have values in this entire range, but we have to find a way to simplify it and also get the best result that we can. So we use this idea of smoothing, right? So we can just take all of the data initially, and then we can just filter out all of that noise, get rid of all of these extra anomalies and these larger and smaller values. Another kind of pre-processing is when you've got extreme values. So what we saw before were just a little bit of noise, but in extreme values, essentially what you have is you'll have lots of these data points. And maybe on one side, this value here is a 2. But let's say on the other side, maybe this is 200. And the problem here is that the scale at which you're using your model will be operating at will make a difference if you have such huge extremes in your data. And so what we can do is we can normalize it. And essentially all that means is that you can just take your data in whatever, however high it goes up to, however small it goes up to, but you can just make it between 0 and 1. So here the idea would be is that this bottom left would be 0 and here's 1. And so you essentially take this data in, however large this is, and we just condense it down. So if we were to just put it down between 0 and 1. And this would help us now look more clearly at the relationships between, our actual data points. Anything that would be close to 0 would be considered small. Everything close to 1 would be considered high, because sometimes we don't care about the actual, the exact values. And so we transform the data to a similar scale, right, between 0 and 1. There's another concept called standardization. And so here, essentially what we want to do is that, it's nice to put everything between 0 and 1, but maybe there's a point, a midway point, that if something is positive, it has some meaning, right? And sometimes when something is negative, it will have some meaning. And that's very common, that when we have models, we have things like classification. And we'll look at that later. But essentially, we can just take the data from 0 to 1, and we can shift it. And we can shift it so that instead of being from 0 to 1, it would be in this square from -1 to 1. And anything in the bottom left quadrant, this small box here, could be considered, let's say, a negative class, and everything in the top right could be considered a positive class. And there's standard formulas which you can find, which will help us do this. And this is very, very useful for any numerical data. And we can also use normalization for images. Sometimes images have, really bright spots, some really dull spots. Maybe there's issues in the image itself. So we can normalize and standardize them, especially when we've got, very different wide ranges of images, because it will help us recognize those patterns clearer. Another huge problem with data sometimes is that we have too much of it. We have too much data. So as an example, if you had your data in 3 dimensions, and each of these, let's say, axes had a option of, let's say, 10 positions. So in total, we're talking about 1,000 different positions. 1,000 is not a lot, but we're just using this as an example. The idea is that, well, I have a cluster of these blue points here, these red points here, these green points here, and these yellow points here. But what if I was able to just get rid of one of those axes? I can still have my my red points, my blue points, my yellow points, and my green points, but I've got rid of an entire axis. So what I'm left with is just 100 positions, and this is just an example. But you can see the difference. We've reduced the amount of data that we're having to store by 10 times just by using this simple technique. And we can go further. We can go from 3D to 2D to 1D. And here it would be every single value every data point has a single value. Right? So 10 different positions, and that's it. And so here we've gone from 1,000 positions to just 10, reduced our data by 100 times. And that's huge improvements, because sometimes our data is very large and we just can't store it. And when machine learning models are working on all of your data, it's very common that your data, because it's too large, it takes too long for your model to run. And what you'd want to do is find ways that you can take your data in these large dimensions and you can bring it down to smaller dimensions, but you want to preserve this idea of the distributions, these different clusters, that you can see them clearly. Because in here you see that there's some overlap between the red and the green and the yellow and the blue. And there's different techniques that help us do this. If anyone's interested, I would look at PCA. It's a very, very useful technique which helps us take any kind of data. It doesn't just have to be numerical, but it tries to find out what is the best way that we could basically split up our data so that we can still observe, the different relationships clearly, and not like this here, by reducing the amount of data that we're using to store it. The last kind of data, the problems that we may encounter, are with categorical data. So categorical data is a little bit weird because it's not necessarily just text. So as an example here, I have a data set of tips. So it stores a group of people when they go to a restaurant. What was their total bill? What was the tip they gave? What was the sex of the person who paid the bill? Were they a smoker or not? What time of day was it? So was it a lunch or a dinner meal? The time was, I believe in this example, it was a Thursday, Friday, Saturday, or Sunday. And size was the number of people that were present in that, in that meal. And the problem here is that we have so much of this categorical data. Because let's say smoker has either true or false, or it has 1 or 0. We want to find a way that we can essentially turn it into numerical data, so that being a smoker means something and not being a smoker means something. Because when you're working with your data, you want to have a way that you can understand different relationships, with your input data. So let's say whether they're a smoker or not. And in this example, what we would do is, instead of having, a single variable for whether the person, smokes or not, where you'd either have a true or false, we do this procedure called encoding. And encoding lets us go from having just a single, variable called smoker, and it could be either true or false. And we could have, say, 2 new variables. So whether a smoker or a non-smoker. And here the idea would be is that, yes, each of these could be true or false, and we would be increasing the data, but now we can look better at the relationship between not smoking and smoking. With two different values, so true and false, this is something that will be more easy to do. But let's say with the time, so if you're giving an option of having days between Monday and Sunday, converting that to numerical data might be a problem because you don't want to necessarily give Monday as a 1, Tuesday as a 2, Wednesday as a 3, because what you're saying is that Wednesday has 3 times the importance as Monday now, and that might not necessarily be the case. So instead, you would have 7 new columns: Monday, Tuesday, Wednesday, Thursday, Friday, etc. And what you would have is you'd have either a true or a false for each of them. So if it was a Wednesday, you'd have if you would have a Wednesday, you would have a false in every column, except for a true in the Wednesday column. And that way we can deal with this categorical data. I'm just going to check the chat because I see we have a couple of questions. So the first one was regarding normalization and standardization in terms of having to deal with extreme values, or do you choose one of them? It's very common that we use both. So normalization is something that most people will do on any kind of data that they have, because normalization will always get rid of the very extreme values. Standardization is not used as much in small problems. It's more so for when you've got larger classification problems where you want to have a relationship between positives and negatives. And the question was asking about PCA. So yes, PCA stands for Principal Component Analysis. And the main way that it works is that if you were to give it lots and lots of data, so we can visualize in 3 dimensions, right? Because that's the world that we live in. But it's very difficult to imagine 4 dimensions or 5 or etc. So imagine you had data with 1,000 dimensions, and it may sound strange to hear that, but just imagine you have a survey, and you have 1,000 different questions or 100 different questions. Maybe you want to know which of the questions are the most important at helping you predict the value that you want, or to get that understanding of what you want from your data. And so we can use this idea of PCA, Principal Component Analysis, to look at the main components. So those are the most informative features, the most important questions in that survey that are going to help us preserve this, like the relationship between the different clusters, reducing the amount of data. But of course, we don't want to have this problem where we're losing too much information and now it's difficult to understand from our data. And so in the data set that I was talking about with the tips, you can see that if I was to plot the different numerical features, and this is the second thing that you would do always once you've looked at your missing data, is then to plot the different features that you have. And if you've got many, just plot the most important ones. So here I'm plotting the total bill, the tip, and the number of people that were present at that bill. And you can clearly see that majority and lots of the data that we have, the bill wasn't very high, and the tip wasn't very high, and there was usually about 2 people, right? So 2 people coming to dine, and it was very rare that there were 5 or 6 people. And similarly, when the tip is very large, but we can use the different relationships between the bill and the tip and the number of people, let's say as an example, to predict what it will be the estimated tip based on the number of people and the total bill. That's just an example. And what we were talking about earlier was this categorical data, where you have these issues of it's not as simple as you have a number which means something, right? So 2 people at a meal means something when you compare it to 6 people at a meal. But lunch and dinner, whether you were to give it a 0 or a 1, it doesn't make as much sense. And so that's where we use the idea of encoding. Encoding in this way would give us, 2 new columns, one for lunch and one for dinner, and every person who has every bill that was a dinner, say, would have a true in that column and a false in the lunch column, and everyone who had where it was a lunch a lunch meal, they would have a true in the lunch column and a false in the dinner column. Before we move on, are there any other questions regarding data and data pre-processing? I know it's a lot to take in, and maybe going fast, but this will be recorded, and of course, you'll be able to go back and go through. I think we'll move on. So there are three main types of machine learning models. You have this concept of supervised learning, and this is where we have data. We have labeled data. So imagine when we had our images of dogs, we actually have labels to tell us that, there are dogs, and let's say here is where the dog is in the image. In unsupervised learning, we don't have those labels. So we have data, we have whatever it may be, but we don't have those labels. We don't have an explanation for our data. And the third kind of machine learning models is reinforcement learning. And it's a very, very different problem. It's like a completely different subsection of machine learning, but it is very common and it's used a lot in the large language models like your ChatGPT and your DeepSeek models, etc. So if we were to go back to when we talked about the numerical data, we looked at this concept of, as you have another value of x, you could predict the other value of y, what it should be. And if you were to take y is equal to 2x, we could predict very accurately what the value for y should be. If x was 6, we know that y should be 12. But say that our model wasn't so perfect. Say that in our model, we didn't have 6 as y and it was 7. Well, maybe then, instead of saying y is equal to 2x, maybe our model will say that, well, it's going to be y is equal to 2x minus, say, 0.5. Or sorry, plus 0.5. Of course, it couldn't give, exact values, correct values for everything, because the model will try to understand the best it can the relationship of your data. So say now in this example, the data point for 3 will be up here, right? Because it's 7. And so now if I was to take this model and I was able to predict or to get an estimate for how good is this model, right? So this is my model, y is equal to 2x plus 0.5. And it's a very simple model, right? Because it's just an equation using two different features, x and y. Or technically, it's just using the x to predict the y. When we look at this, the graph, right? So the line that goes between all of these points is the model. We can compare where each of these points was in relationship to what we saw in the y values that we had in our table, and we can compare them. So actually, just for simplicity, let's get rid of the plus 0.5. What you'd have is that, well, this one is perfect, right? There was an error of 0, right? Because it was perfect, there's no difference. And here we have 0 as well. And for these two up here, we also have 0. But for this one, the error is now 1, right? Because we've said that it's y is equal to 2x, so we've got y is equal to 2 times 3, which would have been 6. But we're now saying that it's 7, right, just for testing. So now you've got this difference of 1. And you could consider that your model, essentially, how good it is how many errors and how large the errors are in your when you compare your predictions to the real values which you initially had. And in this case, you only have an error of 1. The total error could just be 1 across everything. But you can imagine that, let's say we had more data points, that this error could be much larger, depending on how different your predictions are from your observed values that you had in your data set. Now, if I go back to where we were, this is the same concept here. And this is what we would call a loss function. And that's the only important thing to remember, is that these loss functions are ways in which that we can go from taking a model, looking at its predictions, compared to the actual values that we got, and it will give us a performance. How good was our model at predicting the values, right, compared to what we initially got? And that's all this graph is showing here. The green squares will represent the actual values, and the blue line is our model. And if we look at the red line, so that's the differences between the observed values, the green values, against the model, the predictions, we can sum all of that up together, and that will give us, let's say, a value called E, our loss. And what we want in our machine learning models is that we can minimize this value of E, right? Because we want the best model, which has the least amount of errors. But we need to have a way that we can train our models and we can tell our model when is it good and when is it getting worse. Now we're going to talk about some of the different concepts beyond just how models can be trained to get better, and we're going to look at the different types of the different components that we consider when we're working with machine learning. So the first thing is this idea of bias and variance. In the top left, what you see is a very good model. The predictions are very close together and it's very accurate too. In the bottom left, what we see is that, yes, the predictions are close together, but they're off, right? They're not close to what the target, the bullseye is. In the top right, what we see is that, well, the points are generally close to the right answer, but it's too much of a spread, right? There's too much variance. Variance would refer to, how spread out the data is. Your predictions are, sorry. And in the bottom right, what we see is the worst one, right? We've got high bias and high variance. So the model is not very accurate, it's not close to the bullseye, and it's not even close to a specific area. And what we want to do is very simply, we want to make our model the least complex that we can have it, that will give us a good trade-off, right, between error and between bias and variance. Because when we have this like optimal line, is that when we will have the least amount of error. So as an example, if you're predicting people's heights using their weights, you don't want to increase somebody's height by 10 centimeters just because they are 1 kg heavier. That would be a really big problem in that your model has very high variance. And at the same time, you want it to have low bias too, because if you increased, let's say, their weight by 0.1 kg, you also wouldn't want it to impact the predicted height by too much. And the reason why this is important is because what you'll have sometimes are these two kinds of problems. So underfitting and overfitting. So if you imagine we were to plot all of our data, if you had a model which was perfect, so it connected every single data point together, so no matter what value of X you gave it, it gave you the right value of Y. Whilst you would have a perfect model at getting predictions, this is a model which has very high variance, meaning small changes in X result in big changes in Y. And that's not ideal, because if we were to zoom in into a specific section of this graph, there'd be a huge difference in how the model is predicting from one to another. Similarly, with underfitting, what you have is that when you take any value of X, no matter if it's small or large, it just gives you the same value for Y. And so here's an example where we have high bias. So the problem is that, well, the model may be on average not too bad, right? Because let's say for some of them it's more correct and for some of them it's further away. But it's a very, very simple model. It's just giving the same value, the same prediction every single time. What we want is this idea of low bias and low variance. You want it to be able to be quite accurate, but you also want it to not overfit too much, where you're capturing the distribution, the pattern in your data, but not too much that it becomes unrealistic for if you were to give it new bits of data. The next thing to consider is that when we use why overfitting, so there's a question, I'll just go back. So why is overfitting not ideal? So the problem in overfitting, let's say, would be, say I was to take a value of X right here. So the model would have predicted what's on the red line. And maybe if in this situation, it wouldn't be too bad, right? But let's say you've got the X value here, right? And so it's going to predict this value here. In these examples, it might be fine because, of course, these are between the two different values. And in general, the model, if you were to just draw the average, it's going through this arc. So any value within this range, it might be okay for. But the problem would be if you've got X values less than this or X values greater than this. Because whenever you have machine learning models, the goal is that they are to be used for new test data, right? So you build a model so that then you can test it on something you haven't seen before or something that you haven't observed. And because of this, like the model won't just stop here. Maybe it jumps up to here on the next step, right? Or maybe it drops all the way back down here. And this is an issue where it's like your model isn't what we call generalizable, because if you were to give it new bits of data, it'd be really bad. So as a simple example of overfitting, if you were to have different images of dogs, of let's say just 2 or 3 different species, it might be really good at those 3 species, but let's say it overfit. It would only ever be good for those 3 species and not anything else. And with underfitting, the idea would be that, oh, it doesn't matter what species of dog you give it, it will pretend as if it's all just one species, one breed. And so what you want is this good balance where your model performs quite well, right? And it's also explainable. Like you can show somebody, roughly as you increase X, this is what will happen to Y. So it's not a perfect model, but it's generally quite good. But you can also expect that the model, let's say, would come down like this. So if you were to give it new values of X, it would have a reasonable performance for Y. And you wouldn't have the issue of jumping to extremes when you're overfitting because you can't control this overfitting. Moving back, so this next thing that I wanted to cover was to talk about into more detail about this idea of training set and test sets. When you have your data and you're using a machine learning model, you need to set aside some amount for training. And what we use with the training data is that we just build a model that's able to, start to learn and start to understand what is the task that we're trying to solve. But the problem is that models can overfit very easily on your training data. And so what you need to have a way of checking how good your model is when you were to give it, if you were to give it, unseen data that you've never given it before. So the concept is that if you take, let's say, your data and you imagine your data is represents, the full data represents 100%. Then you could split it up. So let's say your training data, your training set is, let's say, 70% of your data, and your test set is the remaining 30% of your data. In this example, right, what you would do is you would train on all of the 70%, and at the very end, you would just test it on 30% of your data, and then you would look at, whatever metric you had that would tell you how good your model is, how close you were to the right answer. And the reason why we have this validation set, this other set in the middle, is because when we're working with large amounts of data which have different features and there's different let's say categories of data, and we want our model to be really good on all of them. So as an example, you want your model to be good on different ethnicities, different genders, etc. Different ethnicities, yeah. What you don't want is that it's really good at some and really bad at others. What you want is that it's generally good at every type of group within your data. So what we do is we can't just train it and then test it at the very end, because otherwise, if we were to just keep training and pick whichever one is the best on the test set, right, so whichever gives us the best test score, we'll fall into the issue where, again, you may just be overfitting for your test set. So what we do is that we can split up that training set. So initially you had, let's say, 70% of your data set as your training set and 30% as your test set. You would now take that training set and then split it up again. So in this example, we split it up into 5 different sections. What we're going to do is we're going to train on these 4 in green, and then we're going to test it on the red, this validation set. And we're going to do the same exact thing, right? So we're going to train on all of the green, and we're going to test on this red validation set. And we're going to do that for every block. So every of these, these different sections of the data set. And you can see by the end of it, what you've done is that you've tested on this part of the data set, right here. You've tested on this part of the data set here, right? And so on and so forth. So what you've done by the end is that you can take the average validation score. So the average score on this, this validation subset and this one all the way down. And by taking its average, you can get, a good estimate of how well your model was on your data. And the benefit is that we can look at these different validation sets and we can see, let's say in one of them, it was only 60% accurate, right? So in one of these splits, so let's say in this one here, it was only 60% accurate on the red. But in this one, it might be 100% accurate. And so now maybe we'd want to look into more, why is it that 60% is so much worse, or why is the 100% so much greater? So we use our data, we can train it and we can test it, trying to maximize that average validation score so that we know, how well our model performs on different groups, on different parts of the data. And then you take the very best model at the very end, and then you can put it against the test set and see how good your final model performs. And we'll look at an example too. In supervised learning, we essentially have 2 main tasks. You have classification problems and regression problems. So classification is when you try to assign classes. So that's different categories. So let's say here we've got green dots and cyan dots. And all you're trying to do is decide on different options. Regression is when you're trying to predict a specific value. So like given some data, can you predict a specific value, something new? In the tips dataset, the one that we were looking at earlier, what I've done here is that I plotted all of the different features, right? So the total bill, the tip, the sex of the person who was paying the bill, whether they were a smoker or not, etc. And what we can do is we can look at the correlation. And by looking at the correlation, we can say, well, of course, the diagonal will always be 1 because a feature, when you compare it against itself, will always be 1 because it will be the exact same value. If one goes higher, the other one will go higher. If one's lower, the other one is lower. But what we can do is we can specifically look at the sections, the parts of our correlation, which are darker. So, in this case, more red, which means they have a higher correlation. And it makes sense, right? So here we see that the tip has a higher correlation with the total bill than say whether they are smoker or not, right? In fact, smoker has a very, very low correlation, meaning it doesn't make much of a difference. And we can use this information and we can plot it here as well. That will just give us a little bit more information. And it will tell us maybe what certain features are more useful to use. And the reason why this is important is because when you have your machine learning pipeline, once you've got your data, the next step is that you want to extract the features, right? So what are the features that are most important? And here you can use PCA, you can look at different ways of reducing the data. You can look at which features are most important. These code snippets are inside a notebook, which we'll show at the end. And when you take the most important features, you can build your model on those features, and then you can test it at the end on your test data set. Once you have a model for, let's say, classification, you'd want to have a way that you can accurately, get a sense of how good the model is. And so we have these lots of different metrics. So if you were to take, it doesn't just have to be 2 classes. So here we've got positive and negative. So you can imagine, this is whether a person has cancer or not. But you can take all of what your model predicted against what the actual values were, and you can just put the numbers here, right? So how many were true positives, false negatives, true negatives, etc. And you can use these different metrics, and each of these will be good at specific things, right? So accuracy is a very common one, but it's a problem when, when you're comparing it on a data set which has imbalanced classes. So let's say there's only 1% of the population which has cancer, and your accuracy is 99%. Well, that's a problem because you haven't looked at how good your model is actually at detecting cancer, which you might want to use, this metric here. Or let's say how good it is at, not giving false negatives, meaning when you're saying somebody doesn't have cancer when they actually do. And also the idea of specificity, where you're looking at, well, you don't want to tell people they have cancer and when they don't actually have it. So different metrics can help us to look at different areas of how good our model performs. So if you imagine here very, very simply, we can just look at the tip data set again, and we can just class them into different, based on if it was a low tip or a high tip, and we can, just plot it, and we can see, well, this model performs quite well on, when it's a low tip, but when it's a high tip, you can see that there are some issues, and we can use the metrics to help us look at, where are the issues in our model and what could we focus on more. So there's a question, why do we already get the evaluation on 70%, but additionally use 30% data to evaluate it again? So the reason why we do it here is because we need a way to know how good our model is. Because let's say we were able to build 5 models, we don't want to test all of them on the test data and then just take the best one, because that one might overfit on the test data if you always were to do that. So what you do is if you evaluate it on the training data, let's say you've got 10 different models that you're testing, you can take the best one and then you can evaluate it on the test data. And it's just simply because you want to know how well the different models that you're experimenting perform, but you only ever want to test one of them on the final like holdout test data. So the data that you never gave any information into your training data. Otherwise, yes, you'll have the issue of overfitting, and yes, to test if the model generalizes well on unknown data. Last couple of slides. So classification can also be used to have multiple different classes in the same image. So we're not just looking at, a single image and what's there. We can look at, different vehicles and where they are in the image. And obviously this is a little bit more of a difficult task than just deciding whether, there is a dog in this image or not. In unsupervised learning, we also have this idea of, you have these different data, could you put them into clusters? So could you say that, this is one class, this is another class, and this is another class? And this is really important because sometimes you have data and you want to group them and you want to understand, the different groups of your data, but you're not sure what those groups might be, right? So as an example, you're looking for if somebody's low risk or high risk at something specific. You may not know why somebody might be low or high risk, and you just want to experiment. So you can use this idea of unsupervised learning, where you just put it through different algorithms. And so this specific algorithm here is k-means clustering, and all it does is it tries to group the values which are close together, so that it can give you roughly, based on the number of symptoms and how severe those symptoms are, how serious is your illness. And that can be quite useful. We'll move on to reinforcement learning. In reinforcement learning, the idea is that you have an agent, right? So this is something that you have that you're letting, experiment an environment. And it will perform actions in that environment. So you could imagine this as just a very simple robot, right? So this robot, it has a choice of, let's say, going towards the water or going towards the fire. So the actions it could perform, right, is either moving left, where it would go to the fire, or moving right to go towards the water. And then based on, taking that action, right, we have a model which is able to basically tell the robot, oh, you've made a mistake, and you can give it a reward or a penalty, right? So in this case, we're giving it minus 50 points. And the reason why we do this is because you can basically just trial and error, for millions of times with these random agents which exist, in an environment that you've created, and you can just let it just test. And what it will do is over time, only the best actions uh, will succeed. So eventually, the robot, the agent, will learn not to go towards the fire and instead go towards the water. And as an example of where we see this, well, it's used in lots of language models. So reinforcement learning, we could use it in a way that, if a model gives us a response in a format that we like, we reward it and we tell it, keep responding like that. And over time it will get better because it will learn to continue to, seek those rewards. Obviously they're not real, anything real. It's just uh, hypothetical. And you can imagine here when you're playing chess too, right? So different chess bots that you can play against and that exist, they just look at all the different moves. And what they've done is they've just learned again and again, which are the moves which help them perform better, maybe get a higher score, maybe result in winning the game, and which are the ones that they should avoid. And so obviously, as a result, it will learn to not make mistakes and it will learn how to do better moves. Main last area that I wanted to mention was prompt engineering. And so this is something that another entire workshop could be done on it by itself. But the problem is that because there's lots of tasks which are difficult to learn, and one example is writing code, there's ways that we can leverage the different tools that we have, these different AI tools that can help us to, let's say, do those tasks that we're not experts in. And the steps, the main things that you want to focus on is that, well, first you want to pick, a suitable large language model. So when you're writing code, there's already models which are integrated in these different websites that you can use. And Google Colab is one that we'll look at later. You've got ChatGPT, of course. You've got DeepSeek, which you can put on your own computer and that's free, etc. But this is the easy step. This isn't very, very important. The important thing is how you give it prompts. So almost all language models, you'll need to give them these like detailed step-by-step instructions. And if you don't understand something, tell it, explain it to me like I'm a 5-year-old. When you're asking it to write code for you, tell it to use comments. So comments are just lines in the code that, programmers will add to help us, to help others and ourselves when we go back to it after a long time, to remember what was that piece of code doing? Like, what did it mean? And we can tell, these large language models to explain it, to give us these comments so that it can explain its thought process. Different kinds of these words and these phrases we can use when we ask it to help us write code, to produce better code that is more useful for us. And obviously, when you do use it to generate code, you want to be able to understand every line of code, right? Even if you don't understand in general, what the code does, from the very beginning, try to understand each individual line. And if you don't understand, ask it to explain, what does that line do? And slowly you'll be able to understand, okay, well, now I understand what this function, this program is doing. But as a reminder, I would say, obviously, it's not a replacement for not learning how to code, because there's a lot of things, a lot of problems that occur when you're using these models. And not knowing how to code sometimes means that you can't fix them because you don't exactly know where to look for. And so whilst it's a great tool, especially at the very beginning, and it's a great teaching tool, it's really good if you want to use it to help teach you, how to code and how it works. You should still, of course, if you're planning on doing work in the area of machine learning, you want to be able to still learn how to code, right? And there's many YouTube videos, many courses online that are free that you can use that just explain things, right? So one very good example is W3 School. I put it in the chat. It's just a resource that has lots of information on different programming languages, on how you can learn how to code. The final thing is that when it comes to the building a machine learning pipeline, we essentially have these 5 main steps. So the first step is that making sure that you understand what problem you're trying to solve. Because sometimes machine learning and AI is not the most suitable solution. Even though we like to talk about AI and it might be nice to make something that uses it, sometimes we can use a much simpler model and we don't have to use something that's so complicated when we're trying to build this pipeline. You want to make sure that your data is as good as possible, and that involves obviously collecting that and processing it, etc. And you want to make sure you remember again what predictions you're trying to make, because you need to pick the model that will give you the output that you're trying to get. So if you're working on a classification problem, you need to look at what are the different classification models that are out there. Same thing for regression. Same thing if you don't have labeled data and you're thinking about using unsupervised learning, you want to look at what are you trying to get and what kind of models are out there that you could use. Um, And the last thing is that once you've produced a model, try and test it and update it as much as you can, because it's very easy to build a model. It's very, very simple to put it through code and try to get a model that is able to work on your training data and maybe even your test data. But you want to be able to continuously give it more unseen data, whenever you can, to see how well does it perform now. Because maybe data was different 5 years ago from when your data set was initially collected, and now it's different now. Um, Things have changed, and the what we observe in the real world is different. So you need to test it and you need to update your model, right, so that it stays relevant and accurate. So there is a repository, and I can put the link in the chat. In the second folder for building a machine learning pipeline, there's a notebook file. And using this notebook file, you can download it and you can go through Google Colab. So I think you can click on the PowerPoint here. If not, I will put it into the chat. And this is a notebook which will have lots of information. So it begins by just explaining briefly different important keywords in the Python programming language. And then it goes through some examples. So it looks at that tip dataset, and I've used screenshot from that throughout here. And it will show how we can split the data, how we can process it, and how can we train and test a model. If you have any questions about the notebook, feel free to message. But yes, it was developed in a way that you could do it in your own time. And yes, if you have any questions, you can reach out. I'm adding now the websites into the chat. So the first one is GitHub, and this has all of the other materials as well. And so this contains the information for the notebook and obviously these PowerPoints. And the second thing is Google Colab. So what I'll do is I will show how we can upload this notebook and how we can start to use it. The recording will be uploaded onto the YouTube channel. I've also copied in the link here. I've uploaded the first workshop already. I'll be uploading this as soon as it's done processing. While I set up the notebook, I would really appreciate if you could provide some feedback. And we do have a WhatsApp community where I put the updates on. And again, if you have any questions regarding the notebook, you can always contact. But for now, I'll just quickly go on and share my screen so that we can go through the example that I've developed so far. Again, I can give the feedback link later. Okay. So this is the repository. So what you would want to do is go to the folder for building a machine learning pipeline. And then you want to see that there is a notebook file here. You can download it. And then in Colab, you can upload that file. And basically, this is just a website that you have to have a Google account, but it basically lets you write Python code and run it. And you don't have to have anything installed on your computer. You can use it, and it's very powerful. Once we connect, you can see the different instructions here. And once this is done, we can just click on these buttons here, and we can run code. And there's lots of explanation, and it will explain different types of data and how Python works, and then how we can load the data set, and we can visualize it and then run some machine learning models. And you're always free to use this code, any code that's here, and change it around to be able to produce for whatever data set you would like. And yeah, any questions, feel free to contact either on Teams or on email. And we'll just show at the very end the way that we can produce predictions as an example, right? So here we've got a machine learning model that we've developed in this code above. What we're able to do is we can look at the different tips and the predictions based on the data, this data set that we had here. And again, we can see that we can build a really good model that has, in this case, no errors, predicting everything as we should. I'll end it there. Recording will be made, and I will put it back through this chat later. In the notebook, it does use Python. It's in general the best language, best programming language for working in machine learning to a decent degree. There are alternatives, but this is the one that we found is the best when you're trying to do things with lots of different kinds of data that's suitable for everybody. I will just quickly add the feedback form now, the link to this. And again, I'd appreciate it if you're able to fill this out. And I understand we went a little bit over the 1 hour. And yes, yeah, I know there's a lot of information. I think it will be difficult always to go through so much information because machine learning and AI has lots of maths, and there's lots of different concepts. But I think it's important just being aware of it, and then you can use the tools that the notebook that I've provided, and hopefully use it in your own projects, your own problems. I'll end the meeting now. Thank you all for joining.